是粘贴。
就做那个。
Sto là, i bellissimi giorni, il sole, il caldo. Vabbè, ci siamo quasi tutti in realtà, mancano un paio di persone che non mi hanno detto nulla, quindi sentiamo ancora 2 minuti, giusto 2 e poi vedremo cosa è dare. Mi hanno detto che non ci sono. So since we are 10 minutes late, we can start. So we have 2 speakers today. The first speaker is Sam Frank. He will talk us about collimation and symmetry of the hot blast wave from the recurrent nova V745.
Good afternoon. Today I would like to present this research correlation and asymmetry of the hot blast wave from the recurrent nova V745 scope. Cataclysmic variable is a system in which a white dwarf accretes matter from its companion on the surface of the white dwarf, whereas the Roche lobe overflow a window, and the companion is a mass sequence star. Some magnetic binary is contains a red giant and a compact object, often a white dwarf, where the white dwarf accretes and there is a nebula. Classic nova is a cataclysmic variable or some magnetic binary observed in larger bursts with mass outflow attributed to a thermonuclear runaway. Recurrent nova is a cataclysmic variable has undergone at least 2 nova outbursts since the astronomers started their notice. V745 star was discovered in the outburst on 2014 February. Only 2 previous outbursts had been recorded for this nova. It is suggested that an outburst was missed in the 1970s. V74 star is a recurrent symbiotic nova. At present, there are many evidence that point to the important structure and asymmetry in nova blast wave. Here, the authors analyze the unique structure constraints on the blast wave conditions and geometry using the Chandra data. Chandra carries 5 types of science instruments in this paper. Only the high energy transmission grating and low energy transmission grating are used. For the high energy transmission grating, there are 2 sides grating. One side the high energy grating, and the second side medium energy grating. This figure shows the accuracy rate from the Swift's X-ray telescope observation data. We can see the red lines represent the observation time of LETG, and the blue lines shows the observation time of HETG. We can see the source, the super soft source phase fade quickly, and the super soft source phase only lasts for 10 days. By the time of these observations, they are observing X-ray emission from nova ejector that shocks the circumstellar radiant star wind. Here in the left figure shows the bright emission lines in the V745 star spectra. The figure in the bottom shows the 2006 LS of opposite spectra. We can see the bright emission lines in the V745 star and the 2006 LS of outburst spectra. They are very similar. So the authors fit the spectra of V74 use a model like the 2006 LS of outburst spectra. The LS of is another well-known outburst recurrent nova. This nova is proved to be well described described by an optical scene collision dominated emission. So the collision.
So Ben, we don't understand what you're saying. Fluke is described. What are you saying? Because it's not written, so we don't understand. Can you say it again, please?
The LS of is proved to be well decrypted by proved to be well described.
Described, you mean?
Yes, described by optically seen.
Sorry?
Optically seen. Optically.
Described optically?
Yeah. Optically seen collision dominated. Collision.
Optically seen. Collision, you mean?
Collision dominated plasma emission. So the collision plasma emission model used to fit the spectra of V745 score. Here in this figure shows the best fit three temperature models compared with the HTG and LTG observation data. In this spectra, the data is binned. The authors fit the spectra with at least three different regions at different temperatures. They got these temperatures from the spectral fitting. Here we show the figures of the best fit three temperature model to the HEG spectra. In the top figures, we show the hydrogen-like lines, and in the bottom we show the lines.
Lines,
Yeah, lines. In the bottom we show the helium-like lines. The left is the magnesium lens, and the right is the silicon lens. From the data spectral filter, we can got this model include the velocity broadening of 1,200 kilometers second for once at half maximum, and a blue shifter of 165 kilometers per second. Here is the conclusions from this paper. We can know the X-ray line profiles appear more peaked and triangular than the square-shaped profiles produced by the spherical expansion. The X-ray lines are characterized by the full width at zero intensity 2,400 kilometers per second and full width have a maximum about 1,200 kilometers per second and a net blue shift of about 165 kilometers per second. At the time of the observations, the mean shocked plasma temperature was about 13 million degrees Kelvin. The explosion energy was out of several 10 to 47 erg. So they also confirm another results people have found before, that the V745 score is gaining several 10 to minus 7 solar mass in each nova circle and is likely a supernova present. That's all. Thank you.
Any questions?
And something in your introduction slide, you define the recurrent nova. There is still this definition as a cataclysmic variable, but through the recurrent nova we know, we think about half of them are not cataclysmic variables. They are symbiotic, like B745 fold. So we don't know why, but recurrent novae seem to be common in red giant systems, more than in cataclysmic variables. So that's one thing I wanted to say. And then I wanted to ask you about your last slide, your last conclusion. Why do the authors think it is likely to be a supernova named progenitor? Can you explain that? You said there were even earlier suggestions. What is this about? Last slide, yeah. Confirm earlier suggestion, e.g. Cato. It's gaining 10 to the minus 7, several 10 to the minus 7 solar masses, and it's likely a supernova near progenitor.
And I think they get they fit the spectra, and I think the blast wave, I think it's like the characterization is like the supernova 1A progenitor.
Why? You seem to claim there that it is because it retains mass, but how do they come to the conclusion that it retains mass if they're only observing what has already been thrown out? How do they come to this conclusion? Why?
I think it's I think they are the for the blast wave it's I think it's like the supernova one for.
You said that the blast wave reminds of supernova.
Yes, I didn't.
It's quite different.
Yes, but for this part, I talk about can't get this conclusion. The last part of the paper I didn't talk about it. I didn't remember it very clearly.
Don't remember?
Yeah, very clearly. So.
So I think we should move on. So maybe you can talk in private about
Okay.
this. Okay, so let's thank them. Now second speaker, Christina.
And full screen?
Yes, full screen. Okay. So Sina will talk about black hole regulated star formation in massive galaxies.
Okay, good afternoon, everyone. Here is the paper I'm going to talk today. In this paper, the author try to show how the black hole regulated the star formation rate in the massive galaxy. The first thing they do is select a sample. All the optical spectrum was for the Hubble Urban Telescope Massive Galaxy Survey, and they only use the spectrum with some high quality and rejecting the spectrum with the signal to noise less than 10 and show very strong emission line, especially the H-beta region, because the H-beta region is sensitive feature of the age of the galaxy. Totally 17-fold galaxy was selected. And here is the velocity dispersion. Yes, the black hole mass and the velocity dispersion relationship. They classify 25 objects and with 25 objects with the 25 objects and with the object departing the best fit line and more than 0.2 index as the overmassive black hole galaxy, and also 25 objects and departing for the best fitting line larger than minus 0.2 index as the undermassive galaxy, and the rest 24 objects in the middle and consider them as the standard massive black hole galaxy. And all the stellar mass in this sample was for 10 to 10 to 10 to 12 solar mass, and the strong nebular emission line were removed for the spectrum. And here is this is the sample selection, and the result that they get. The result they apply is first they calculate the star formation history and use the stack-map code and with the mild stellar population model. Actually, these two code and the stellar population model, I'm not so familiar with this part, and if you are interested, you can check the paper and the reference. The result they get are shown in this figure. The first thing is the red line is the overmassive black hole galaxy, and the blue line is the undermassive black hole galaxy. Here we can see that the star formation rate in the very earlier university, the Nobel time larger than 10 gigayear, and the galaxy formation rate on the overmassive black hole galaxy is more intensity than the undermassive black hole galaxy. However, in the recent universe, and it seems the galaxy formation rate on the undermassive black hole galaxy is prominent than the overmassive black hole galaxies. Yes. And the second result they get is here is the cumulative mass fraction. The overmassive black hole galaxy which the 95% of the total mass, more or less here, and in the more than 6 gigayear, and compare with the undermassive black hole galaxy, and they are total mass which the 95% and more or less 2 gigayear, so it's on average 4 gigayear. And so it the overmassive black hole galaxy and the star formation rate is clinched earlier more or less on 4 gigayear, and then the undermassive black hole galaxy. Okay, so this is in order to test their result is reliable. They do many tests, many really. And then the first is the test the degeneracy between the stellar population property and the stellar velocity dispersion. And in this type, they try to allow the stacker map to fit the kinematic at the same time with the star formation history. And the figure in here is the result they get. It also seems that the difference in the star formation of the under and overmassive black hole galaxy is still killing. This is and the second test is and they try to fit the calculate the star formation rate, use different parameter. And first on the model they use is fit the star formation history mu x, and the age metallicity relation mu z equal to 10. And the B and C model is they try to free one of these parameter and fit the another one. And the model D is used another black hole mass and stellar velocity relation. All these four models they use the result I show in this ABCD this four picture. And it also clean to see that there is even though they use different parameter to fit or free different parameter, and the separator between the undermass and overmass black hole is still very killing. The further test is they test the nebular emission and the star formation rate, because at the beginning the sample they select, the optical they use is remove the nebular emission more, because if the galaxy is at a very young age, they will have a very rich H beta. Not only H beta is a hydrogen region, and so in this test they try to include the nebular emission line in the spectrum, and so the result they get also shown in this figure. Even though it's the shape of the star formation line is not so similar with the periods, but it's still very clean to see that the undermassive black hole and the overmassive black hole is decoupled with the star formation history. The further test is the dependency of the stellar population model. Here, the author, they use 4 different kinds of model, including the model they prefer, so totally is 5. But actually, all these 4 models, I don't know very well. So if you are interested in, check the reference. And then I give the result directly, and the figure, this 4 figure is all the result of the 4 model, and they try to use. So it's also very clean to see that the star formation rate and is the difference between the overmass and the undermass black hole is not due to different ingredient in the model they use. And the 5th model is test the galaxy density, and in this test they try to plot the relation between the black hole mass and the stellar with the stellar velocity dispersion with the account for the stellar density, and use this new relation to classify the undermass black hole galaxy, standard mass black hole galaxy, and overmass black hole galaxy, and calculate the cumulative mass fraction again. Here the difference between the over and under massive black hole galaxy, and is still very clean to see. So final test is the selection bias, and here in this image they try to plot the size and the size and the velocity and of the whole sample for the survey, and the sample they selected, and here we can see that the sample they selected is located in a place that more or less comparable to the total population. It didn't focus on only a specific region. Is located in all the place. So this result they guess is not driven by the rejection criteria they select now. Remove the no single to noise spectrum, or the rejected the spectrum with a strong emission line. And so summarize. The supermass black hole galaxy rapidly reach black hole mass capable of clean-chain star formation, and this lead to a shorter star formation timescale in the overmassive black hole. However, the galaxies with lighter central black hole, the star formation history will last longer, and this time delay is consistent with the observed difference in the alpha element over the iron and over of the over and under massive black hole galaxy. And this phenomenon is naturally spreading, and if the clean chain is driven by the AGN feedback, in this phenomenon the accretion rate in the AGN, the accretion rate onto the supermass black hole will lead to more energetic AGN feedback, and then this feedback and will clinch the star formation rate faster, because the energy injected rate scale into the lighter black hole will going at lower accretion rate and would be less effective at keeping the gas corona hot, and then will eventually cool the gas and form the new star. And so this is the paper talking about. So actually here, in my opinion, I have a small question, because all the result, all the image they get, and all the tests they do, all the star formation rate is only located on and night, and this region, and this region, and there is a gas, but they didn't tell about it. Okay, thank you.
Thanks. Any questions? Yes, please.
What do they think? What do they think is the physical mechanism of the quenching?
The quenching, they said that because of the AGM feedback.
Because of
AGM feedback.
Yes, I understand that, but why? What does it do? What does it do?
Nine more or less in okay. If nine the metal will have the metal around the accretion disk, the metal will flow into the black hole because of the gravitational wave, and then if the accretion wave onto the black hole is less, and so this gas, dimetal or gas, they have less time to cooling. So they have less time to cooling. So in this case, they have less time to cool. Cool, yes, and so this so you will get the star formation lower.
Any other question? Okay, so let's thanks Christina again. That's it for today.